All right, good morning. Happy Friday. So, yeah, okay. So this next section of the course is on atomic wave functions and atomic energy and atomic spectroscopy. It's a really short period. It's really a week and a half long. And so our next test will be just over this material, about 4 lectures. And it's very specific. There's a lot of review in it. So today will be a lot of review from freshman chemistry when you went over quantum numbers. So N, L, M sub L, and M sub S. We're going to redevelop those today and talk about the hydrogen atom. We're going to look at the energies that depend upon those quantum numbers. And then we're going to start assigning properties to the atoms, like spin and multiplicity. That'll be very important next time when we get to developing term symbols, because all of the electronic, the atomic energy levels are given, it's similar to those Millikan notations, but these are called terms. They're not called symmetry notations. We can put these wave functions in a character table and define their symmetry, and we'll do that. We'll derive some of the selection rules. But in terms of labeling their energy levels, they use these things called term symbols. So that's really one of the main goals of this section of the notes, is to teach you how to develop those term symbols and to understand them. If you're given a particular term symbol for an energy level, to pull out how many unpaired electrons there are, what is the highest type of orbital that electron is in. And so understanding what's behind that term symbol is a major goal of this section of the course. Okay. So let's dive in. So this is about the hydrogenic wave functions. Now that word hydrogenic, it's an adjective, okay? Hydrogen is the atom, hydrogen is the system, but hydrogenic is a specific adjective that describes really any kind of atom, as long as that atom has one electron. So you could have hydrogenic uranium. There would be 92 protons in the nucleus and 1 electron. So any atom that has 1 electron is a hydrogenic atom. Now, the reason we focus on hydrogenic systems is those are the only ones that we've been able to solve analytically. So just like you did analytical calculus for the particle in a box, you can use those same kind of skills of differential calculus and solve the Schrodinger equation for 1 electron atoms. As soon as you add that second electron, you have electron correlation, and we don't have analytical solutions for that. So 1 electron systems, yes, we can solve those. And so all of the orbitals that you've been taught, the shapes of the s orbitals and the d orbitals and so on, those are hydrogenic orbitals. They kind of fit multi-electron atoms, but we really don't have solutions for multi-electron atoms. So those are all hydrogenic type orbitals. So what we'll talk about is the radial part of the wave function and the angular part of the wave function. The angular part is just, if you think about an atom, kind of like planet Earth, right? You've got the distance from the core to the surface, that's the radial part, the radius. And then the angular part is like longitude and latitude. So we're dealing with a spherical polar coordinate system. So you have an angle down from North Pole, and you have an angle around the atom from the prime meridian over in England, Greenwich time. Okay, so that's the spherical polar coordinate system that we have. And then the radius we can actually change. Can't change that much on Earth. I mean, we have mountains and valleys. But in the atom, the distance from the nucleus is the radial part. And then this will develop into atomic orbitals, and we'll look at their energies. And then we'll eventually, in the next couple of lectures, get to spectroscopic transitions. So let's think about the hydrogen atom. Just the electronic structure of the hydrogen atom. You have a nucleus, a proton, and an electron. And so you have a potential energy term. It's that Coulombic attraction term between oppositely charged particles. So that little bitty e is the charge on the electron, or the charge of a proton. It's that single unit of charge that we have for protons and electrons. It's e squared. It's really positive e times a negative e, because the electron is negative. So that negative sign comes out front. So it's minus e squared. That's the charge piece. Now, one of those, it's hydrogenic, right? So maybe you could have a helium atom with just 1 electron. So that would still be a hydrogenic system. But you'd have 2 positive charges. And so they just pull the number of protons out front, and that's what Z is. So Z in this equation is the charge on the nucleus. And so we pull Z out, that's the number of protons in the nucleus, we have twice the charge. And then down in the denominator, we have the distance, the radial distance between the electron and the nucleus. Now you might think, wait a second, I thought everything was being done with waves. Right? And so this would be, again, that radial wave function part. So that would be R in the radial wave function part. But this shows up, this distance shows up in the wave function, and it also shows up in the potential energy term. So we're still going to have to solve this equation, or we won't actually, but in theory you'd have to solve this equation with respect to R. R is in the wave function, but it's also in the potential energy. And then there's 4 pi epsilon naught. That epsilon naught is known as the permittivity of the vacuum, and it's just how electric fields propagate through a vacuum. So it's just a scaling factor that corrects it for the diminishment of charge with respect to distance in a vacuum. Then there's the Hamiltonian piece, and we see that V term is the potential energy. Then you have the kinetic energy term. And so this is the kinetic energy term that we were familiar with from the particle in a box. And then this is the potential energy term. So that's the full Hamiltonian minus h bar squared over 2 mu. And then that upside down delta, we call it del, that's the second derivative operator. So we take the second derivative across all space. So in our particle in a box, it was just the x-axis. But in this case, it's 3 coordinates, and it's the radial distance, and then theta and phi, the longitude-latitude angle, and then the polar angle. So we have all 3 of those coordinates, and so this would be a triple derivative. And so we would do a partial derivative with respect to r, theta, and phi. Now this mass is the reduced mass of the system. So we have a nucleus, and we have an electron. And so this is the general form of the reduced mass. It's 1 over the reduced mass is equal to the sum of 1 over all of the masses. So you just have fractions. So 1 over the mass of the proton plus 1 over mass of the electron. Now think about how you would add fractions. You'd have, say, 1 over 4 plus 1 over 2,000. Does the 1 over 2,000 add much to the 1 over 4 piece? No, and so this is similar to an electron. The proton is about 1,000 times heavier than the electron. And so it's like you have 1 over 4 plus 1 over 2,000. And so then really the fraction is 1 over 4. So essentially the reduced mass is the mass of the electron orbiting the nucleus. So the nucleus is essentially stationary, and for the approximation, or good approximation for solving the Schrodinger equation, is just to use the mass of the electron. And so here's the Schrodinger equation written out with the wave functions in there. So we have the Hamiltonian that we've defined, but we haven't defined the wave function. Now this wave function, we have a nice situation that it turns out that the radial distance is separable from the angular behavior. So we can break this into 2 wave functions. We can have the wave function made of 2 parts, a radial part where we have a radial wave function, and then an angular part, which is just how it changes with respect to angle. This angular part is, the solutions for this came from the spherical harmonics. And so we'll talk a little bit more about what that means, the spherical harmonics, when we get to the shapes of the orbitals. But the radial distribution is just a simple one-dimensional particle problem. You can solve this problem as if r goes from 0 to infinity, and you can solve the Schrodinger equation separately. That's what we mean by separation of variables. We can break it into 2 problems, and we can solve it with respect to the angular dependency, and then we can solve it independently with the radial dependency. As it turns out, when we solve for the spherical harmonics, another term appears in the potential energy that's based upon the angular momentum. So as we get more and more angular momentum, more and more changes with respect to angle, then a term shows up in the potential energy, and then we can use that term to get an accurate energy from the radial part of the wave function. So here's the full Schrodinger equation. So let's go back into the lab and solve this by hand. Okay. So we could do that, and you probably will do that if you go on to graduate school. This will be your first quantum mechanics course. These should probably be about 10 weeks in, where you saw the hydrogen atom Schrodinger equation, and it would definitely fill this board, and you might end up on that one. Okay. And so we had to do this. It was really funny, coincidental. My best friend and I, we were working through it together on the chalkboard, and we had it all written out. And this HP had a production plant in Corvallis, Oregon, where we were going to graduate school. And they just showed up on campus with some photographers, and they wanted to take some pictures of some sciencey looking stuff to put on the cover of their calculator manual. Okay, and so they were doing a new scientific calculator, and they wanted a nice sciencey picture on the front, and they saw our chalkboard full of the hydrogen Schrodinger equation, and they're like, this is it, you know. And so they said, can we take a picture of your work? We're like, sure, go for it. And so they were taking pictures, and they're like, so what's this? Is this like a recipe for a bomb or something? And my friend goes, you could say that. And so they were like, oh dear. So it was funny. It wasn't a bomb. It was just a hydrogen atom. It was an electron. Yeah. It had nothing to do with the nucleus, though, so that wouldn't even work. Yeah. So this is never mind. So this is all. But you see all of this capital R with respect to little r here. Those are the radial wave functions. And so out of that comes this energy. So I know I didn't derive this equation. You could say a miracle happens and boop, here comes our energy. It's like the old Far Side cartoon. But we have some interesting features here. We have a new principal quantum number. So I guess you're starting to figure out that we have sort of traditional quantum numbers for everything. So for the particle in a box, we just use n, okay? But in the hydrogen atom, the principal, this is the principal quantum number, and it's also n. It has nothing to do with the particle in a box, so don't get those confused in your head. This is our principal quantum number, and it's what we've been using our whole lives as chemists. 1s, 2s, 2p, 3s, 3p. That 1, 2, and 3 is the principal quantum number. Okay. And it's here in the energy equation from the radial wave function. Even though L is present in the potential energy part of the Hamiltonian, it's not a part of the energy equation. So it doesn't matter, at least for the hydrogenic systems, how much angular momentum you have. Okay, when you add more electrons, then that does become an issue. And so L and M sub L are not in the energy equation for one electron wave functions. So let's look now. When we had the particle in a box and we had mass, where was mass? Numerator or denominator? Denominator. So when mass got bigger, okay, the energies went down, right? And now it's weird. Mass is in the numerator, but notice the energy is negative. Okay, so zero's up here. So when mass gets bigger, the energies get more and more lower. So the same kind of intuition we have from the particle in a box, some really dinky little number line problem, still holds even in a complex system like the hydrogen atom. So now this really isn't that earth-shattering because we only have one kind of an electron, right? We're not going to have a heavy electron. Okay, so this really isn't relevant, but I just wanted to point out that now we see mass in the numerator. Don't panic, it's negative energies. And so this also tells you what our reference point is. Notice our energy system here. Zero is up here at the top. So that would be the reference point for zero energy. And what do you think was the distance between, and this yellow area here, that's that Coulombic attraction. I don't know why they really shaded it, but I guess they wanted to emphasize that this is that function here. So the boundary of this little yellow panel here is the Coulombic attraction of potential energy part. And so you see, as you get the electron closer to the nucleus, the attractive potential drops and drops and drops. And so it's more and more attracted the closer it gets. So what does that tell you about the distance between the electron and the nucleus at zero energy, infinite distance? And so that's going to be our reference point also for Gaussian. So did you notice in Gaussian, all of your energies were negative? whenever you calculated those energies. And it was because the zero for Gaussian is completely separated nuclei and electrons. So it's not really, I mean, I guess maybe out in the outer reaches of the universe, you just have bare nuclei and bare electrons floating around. Okay, so that would be zero energy. And then if we just make even one hydrogen atom, that's negative. So it drops, bringing one electron and one proton in contact with each other. Now we have a negative energy. Making even larger molecules, it's even more negative because you're bringing in more oppositely charged particles and getting them close to each other. So benzene is really negative. Hydrogen's, a little bit negative. So the more big and complex the molecule, the lower downhill it is. So so it's always, whenever you have an energy axis, where do you put zero? For our particle in a box, we just put zero at the ground state and went up from there. As the quantum number goes up, energy goes up. So think about this, it becomes less negative, right? So it ends in the denominator as it gets bigger and bigger and bigger. Okay, the fraction gets smaller and smaller and smaller, which means it gets less and less negative. So as quantum number goes up, down here's 1s, so 1 is the principal quantum number. Then we have 2s, and 2p and 2p, and then 3s, 3p, and 3d, because again, this is a hydrogenic system, and the energy doesn't depend upon s, p, d, and f for a hydrogenic system. And then as the nuclear charge goes up, energy goes down. So what does that mean? Well, this potential energy piece, if you make Z really big, this pit gets deeper because you've got more charges. You got, like I said, 92 and 1 for hydrogenic uranium. Let's look at the radial wave function. This is the wave function. It's really e to the minus r. But what keeps the electron out of the nucleus? This makes it look like the most probable position is at r equals 0, where the electron and the nucleus get sucked into each other. Okay, and that actually can happen. That's called electron capture. So it happens to 1s electrons occasionally in large atoms like uranium and let's see what other kinds of, well, pretty much any of those elements up around uranium or higher. You've got so many protons in the nucleus, and that 1s orbital is so close. Those electrons are going almost the speed of light. And then occasionally, statistically, one can get sucked into the nucleus. Now, what happens when an electron gets sucked into a nucleus?
Radiation.
Yeah, there's a gamma ray released, okay? And if you add a positive and negative charge, kind of eliminate each other. And so the proton becomes a neutron. And so it's really weird. The electron gets sucked in to the nucleus, so that the electron and the proton sort of cancel each other out, and you get a neutron. And then you have a gamma ray that comes out. Yes?
So is that part of why it becomes an isotope and decays over time?
Mm-hmm. This is part of all of those different nuclear reactions. And if you stay with me through the spring, our last section in May, well, really it's April, it's going to be on nuclear chemistry. And we'll talk about electron capture, beta decay. Beta decay is where a neutron spits out an electron and becomes a proton. So the reverse reaction. And so this high-speed electron comes out of the nucleus, and we've converted a neutron into a proton. So there's all kinds of things. You know, we talked about balancing equations. You're always going to have the same number and types of elements on both sides of the arrow. Not in nuclear transformations, but in chemistry, yes. In chemical transformations, yes. But in nuclear transformations, no. You'll actually have elements change their identity by hopping around on the periodic table.
So for years I've been told there are electrons, protons, and neutrons. Mm-hmm. But a neutron really is just a proton and an electron merged.
Well, they're made up of quarks. And so then you can get in there and see that there's different kinds of up and down quarks, and there's like 2/3 of a charge on this one and 1/3 of a charge on that one, and they add together to make a positive charge, a negative charge, or a zero charge. And so, yeah, it gets really wild. It's Alice down the rabbit hole when you get into that. So, but what one other way to explain too what keeps the electron out of the nucleus is that in this spherical polar coordinate system, the volume decreases. And so you've got to take into account the volume element of your system. And so taking into this R squared decrease in volume, the radial wave function goes to 0 at the nucleus because volume goes to 0 at the nucleus. Okay. It's not saying it's impossible for the electron to be captured, because we'll just talk to you about, we have experimental evidence that it can be, but in most cases it's not, because the volume is so small as it goes towards the nucleus that you set up this kind of wave. It has a maximum. It's 0 at the nucleus and 0 at infinite distance, and there's some probability somewhere between 0 and infinity where it's most probable to be. Okay. And so this is a wave function. It's going to oscillate, like waves do, up and down on our axis, whatever up and down means in terms of the amplitude of the wave. If you were to square this wave function, what's the square of the wave function? The term for that? Probability density or probability distribution, either one. And so that tells you where the electron is, right? Probabilistically. And so this is the most probable position. Okay. And so this is plotted as R over A naught, and A naught is that most probable position for the hydrogen, electron. And so this is at 1 A naught radius. It's about half an angstrom for a hydrogen atom. And so here are the radial distribution functions for a lot of the orbitals that we've seen. So here's the 1s. Again, this is in units of the hydrogen radius. So this is the 1s, and it's got a maximum position at 1 radius. And then here's the pin here. You can see the 2s is here in the yellow, and it goes up, and then it has a node. And these have been stacked, so they've been offset, just like you did your spectra, so we can compare them. So the 2s goes up and down and then up again. And so this would be the most probable position. When I say most probable, if you squared that, that would be the tallest part of the peak, and that would be the most probable place. But notice there's this node, and then there's a little bit of 2s electron density that's even inside this 1s. So even as you have electrons far away, they're still sort of in communication with the nucleus. They still feel that nuclear charge. The 3s is way out here. So how many nodes does the 3s have? If you think about the 3s, you just back up to count the nodes in the radial distribution function. If 3s is the third s orbital, the first s orbital has 0 nodes. The second s orbital has 1 node. The third s orbital has 2 nodes. So the 4s orbital has 3 nodes. The 5s orbital has 4 nodes. And so these nodes are radial nodes. So let's look at the picture of that. So here's the 1s, here's the 2s. Notice there's a sort of a gap in there where there's no probability density. So there's some probability density in close to the nucleus and then far from the nucleus. The same thing happens to the p orbitals. So the 2p orbital is the first available p orbital. And here's its most probable position. And so then the 3p orbital is this pink one, and it has a node here. And here's its most probable position. So how many radial nodes does a 3p orbital have? Well, it's not the first p orbital, it's the second p orbital, so it has 1 node. So that's something, those are easy questions for me to ask. It just tells me that you understand how these wave functions work in terms of their radial distribution. Now let's get an idea for scale. So the hydrogen atom, we talked about that red ball in front of target. If that's the proton in a hydrogen atom, then this most probable radius is at Madisonville or down in Spring, or if you're coming east-west over in Navasota or Livingston. So that's how big the hydrogen atom is. And that's just the radius of the most probable position. It actually goes much further than that, you can see. And so this would be Madisonville here. I don't know, which town do y'all go through more, Navasota or Madisonville? So let's say Navasota. I love it because people on YouTube are going to go, what? Okay, and I think I misspelled it, but anyway. It's Navasota, right? Mm-hmm. Sorry guys, for Navasoda. Now, where do you think for sodium up here on the periodic table? That's the 3s electron. So that last electron in sodium is the 3s electron. And so if this is Navasoda, where's this?
Somewhere in the ocean.
Yeah. So, see if I can spell this one. Argentina. Yeah, that's way the heck away. So what do you think about how easy it is to ionize sodium versus hydrogen? Right? We're gonna talk about evidence for all of this by talking about ionization potentials. And so that's a big chunk of the homework, and that's in lecture 3. So we're going to take it apart. We're going to look at the ionization potentials and how easy it is to pull that last electron out. And we can learn about the orbitals by learning about pulling electrons out of those orbitals. So that's a big part of our evidence for this theory being correct. I don't want to tell you the theory is correct and then explain the data. We look at the data and we develop the theory by looking at the data. So let's go through these quantum numbers that came out of this hydrogenic system. So we have the principal quantum number, and those start at 1, not 0. So it's all like one of the first questions you always ask yourself. Okay, I've got a quantum number system. What are the limits? Like in the particle in a box, we started at 1. But in vibration with V, we start at 0. For J, the rotational quantum number, 0. We can start at 0. But now we're at the principal quantum number. It starts at 1. And it can go up to infinity, but you really, I mean, yeah, I don't know. I don't know what the highest principal quantum number I've ever seen would be, but yeah, it's not infinity. Okay, maybe 7 or 8, I don't know. Like in statistics, with population versus sample, 14 is a sample and 15 is infinity, so that's a population. So, okay, so 15 would be infinity. So this designates what shell we're in. And we've also given those names. We don't talk about it that much, but we've given those shells a name or letters like the K, L, and M shell. You hear about that in X-rays. So they talk about the K alpha line from sodium. But we don't. I don't do that much in this class. So we're just going to use the numbers, the principal quantum numbers, and it tells you what shell it's in, like the 1 shell, 2 shell, n equals 3 shell, etc. Then we have the angular momentum quantum number. So new quantum number, you got to know what the limits are. So the minimum is 0, and the maximum depends upon n. This should wake you up, okay? So the maximum angular momentum quantum number depends upon what shell you're in. That's why we don't have a 1p orbital. Okay? You know this, but you don't know that you know this. Okay? So L goes from 0 up to n minus 1. So for a 1s orbital, for the 1 shell, n is 1, and L begins at 0, which is also n minus 1. So we can't have a p orbital in the 1 shell, because that would be L is equal to n, and L can't equal n. L can only go up to n minus 1. Why? Well, it comes out of the Schrodinger equation. Okay. And then for 2, n equals 2, yes, we can go start at 0 and go up to n minus 1. So we can go up to 1. So 0 and 1 in the 2 shell. And so then we have an s and a p orbital in the 2nd shell. And we have an sp and d in the 3rd shell and sp d f in the 4th shell. In the 5th shell, we go sp d f g. But we don't really see g orbitals, but they're there. We see evidence of them in atomic spectroscopy, and you can see them in the NIST atomic spectral database. And then the magnetic quantum number. New quantum number for you, what are the limits? So this one is bound by L. It goes from negative L to positive L, and integer jumps in between. So hopefully you remember from probably high school, this set notation with the curly brackets. Notice the curly brackets here. These are all sets. This is a set of integers that starts at 1 and goes up to infinity. This ... means in like manner, okay? So we go up by 1, and once we set the trend, we have ... which means it increases in like manner with no end. Here we have the far left is the minimum, and the far right is the maximum. And it starts at 0, that's the minimum. N minus 1 is the maximum. It changes by 1, so 1, 2, 3, and dot, dot, dot means in like manner all the way to the maximum. So get used to this set notation, because we're going to use it not just here, but when we get to doing those term symbols, we have these things called the Clebsch-Gordon series, where we start from the minimum, go to the maximum with integer jumps in between. And so get familiar with this set notation. This is how you're going to describe and do your homework and answer the test questions, and it's also how you describe these kinds of things. These are mathematical series. And so then the magnetic quantum number goes from minus L to L. So this is the min, and this is the max. And since we don't know what L is in this set notation, we just have to say minus L plus 1. And then in like manner. So we add 2, then 3, then 4, then 5, all the way up to the max. So it goes from minus L to plus L with integers in between. And then finally we have the electron spin quantum number, m sub s, and that's equal to plus or minus a half. This is the intrinsic spin that they've given the electron. It's kind of unfortunate that they use the term spin, because a spinning charge, it implies a radius, and yet it's very almost impossible to measure the radius of an electron. So what is actually spinning? It's called intrinsic spin because it behaves like a spinning charge. It's a little magnetic. It's like a little magnet. Okay. And so this is with the magnetic spin of plus or minus a half on this scale. So we designate those with arrows, and so we use an up arrow for spin up and a down arrow for spin down, but the up arrow has a magnitude of plus 1/2 and the down has a negative 1/2. So those are our 4 quantum numbers. And we have this Pauli exclusion principle. So no 2 electrons in an atomic system can have the same 4 quantum numbers. So it's like an address. Okay. Every electron has a barcode. It has 4 quantum numbers. And this means that we can't put more than 2 electrons in an orbital. So an orbital has 3 quantum numbers in common, N, L, and M sub L. And then we add an electron, and we add a second electron, down and up. And then we can't put a third electron in there because it's either going to be down or going to be up, and it'll have the same 4 quantum numbers as one of the other 2 electrons. So these are examples of this notation. So if you were given any one of these, you should be able to take this and give me all of the quantum numbers. So this piece right here, we know N is equal to 2. What's L? It starts at 0, so L is equal to 0 for this one. So the s orbital, L is equal to 0. M sub L, it can only be one thing in this case, because it goes from minus L to plus L. And L is 0, yeah. So M sub L has to be 0. And M sub S is ambiguous. It could be plus or minus 1/2. So it could be a spin up electron in that s orbital or a spin down electron in that s orbital. So we really don't know what the M sub S is. A lot of times we put the M sub L down as a subscript, and so in that 4p 0 with 2 electrons, we have 2 electrons in the 4p orbital with M sub L equals 0. The X, Y, and Z, a lot of times we'll put this atomic system in a Cartesian coordinate system, and so we'll have a p orbital along the x-axis, one along the y-axis, and one along the z-axis. So here are the shapes of the p and d orbitals. Let's zoom in a little bit. So here are the Cartesian axes, and now we can talk about what those spherical harmonics mean. I think I've talked about this before, but let's go ahead and let's draw the one on the left, 2px. going to be hard for me to draw. Let's look at the Z. That'll be a little easier for me to draw. Okay. Let's see if I can get this arranged. Let's zoom in. Okay. So if this shell, if we come along, and this is the spherical harmonics, so picture a metal shell, not a metal sphere. That would be hard. I mean, it'd be solid. It would vibrate the same way. But let's think of a thin shell, okay? And I whack it on the top of the hammer. It's going to oscillate. Now I've whacked it on the z-axis, and so it's probably going to oscillate on the z-axis. But we're not going to let it translate. So somehow we're holding it in place. So the shell is deformed. It's undergoing a harmonic oscillation. And so what would that harmonic oscillation look like? Well, if I whacked it on the z-axis, it's going to dip down and bulge out at the bottom and oscillate like that. So it's going to go like this along the z-axis. So if I stood at the nucleus and I looked this way, what would be the change in the y direction if it's oscillating on the z-axis? Right. And so over here in this coordinate system, if I plot the change as a function of the angle, so I'm looking out at this direction, I see no change, and so I put a dot at the origin. If I look up here at 45 degrees, so I've come up now 45 degrees, and I look at the change, I see it's negative, right? It's closer to me. Okay. And so I'm going to go this direction, and I'm going to plot this, but I'm going to call that a negative number. And so this is the change. So this piece right here is what I'm plotting, right there, and it's negative. It's negative deflection. What if I look straight up and I plot this deformation right here? It's a bigger number. So it's further away from the origin. And it's negative still. If I go over here and plot that, it's a little closer to the origin because it's less of a deflection. You see that? Less of a deflection. And so I plot it at this angle, and it's not as far out as the top piece was. It's further in, and it's still negative. And if I look back this way now, I'm looking in the opposite direction, it's back to 0. So if I connect all of these deflection points, I get this shape on top. And if I go this way and plot down here, I get deflection and it's positive. I look straight down, that's the most deformation, and it's positive. And I look over here, and I plot that point over here, and it's also positive. And this, I get this shape here. So what I'm plotting here is the deformation of a spherical shell. It's a harmonic motion of a spherical shell. And where's the motion? It's where these lobes are. So this picture that we draw is the deformation of the electron cloud. I think that's important to go ahead and take the time to think about what these images portray. Okay? Because people often look at this and say, well, how does the electron get from this side to this side when the nucleus is in the middle? You're confused as to what this is plotting. Okay? It's an electron cloud that's surrounding the nucleus at a distance, and that cloud's oscillating. So it's a wave function of this cloud, and we're plotting the deformations of that cloud. Now, if we square this, the negatives become positive, and they change their extent a little bit. And the square of the wave function is the probability distribution. And so this would tell you that this electron in this orbital is spending its time on the z-axis. And so it's going to bond with things on the z-axis. And then the x would be on the x-axis, and the y would be spending its time on the y-axis. So kinetic energy, where it's changing, when you square that, that's location. So wherever the wave function is changing, that's where location is when you square it. Does that help with these pictures? So let's go back to the photos. And the book. Okay, so this is telling us then that this 2pz orbital, the electron cloud, is oscillating on the z-axis, and oscillation is location. And so that's going to bond with things on the z-axis, or interact with things on the z-axis, and the x and the y. So the p orbitals are super easy because they lie right along the axes. And the s orbital is easy too because it goes the same in all directions. So the oscillation for an s orbital is it's totally expanding and totally contracting. So when we shade them in, we're just shading one particular slice in time. It's deflecting in or deflecting out. So if I draw it red at one time, it's going to be green at another time if I'm using red and green to show deflection in or out. Okay. And like here, or yellow, gold, and blue, you know, the s orbital would be all gold or all blue, depending upon if it's expanding or contracting. Here are the d orbitals. Let's see if we can understand these. Now I have you practicing your artistic skills. I want you to draw these yourself in your notebooks and try to do a great job. I mean, you don't have to use shading and everything, but you know, do your best to draw the coordinate system like I've drawn here and draw the orbitals on there. Use these pictures as a guide, and be sure to label the symmetries so that you understand when you draw them with your own hand what's going on. So let's look at these a little bit. We have symmetry designations along with all of them. So let's start with these three, the dxy, dxz, etc. So here's the dxz. So let's look carefully at what this means here. Again, that's x times z. So we have here the x-axis right there and the z-axis right here. And so we have positive x over here, positive z up, negative x, and negative z down here. And so this right here would be positive x, oh, wait a second, stop that. Positive times positive. So this is positive. And then here we have positive z times negative x, so that's negative. And then down here we have negative x times negative z, so that's positive. And over here we have positive x times negative z, so that's negative. So you see that shading is that function of x times z. Now this is an orbital that has two nodes. These nodes are planar. And so we have expansion. So if you were to draw the deflection of the electron cloud, let me just do this, x and z. It's deflecting here and shrinking there and deflecting there and shrinking there. So it's positive here, negative there, positive there, and negative there. And it's not changing right on the axes. So it's squishing, and it's squishing like this one direction one time and squishing like that the other time. So it's doing that. And that's a higher angular motion than just squishing one direction or the other. So the P is just squishing left and right, but now it's squishing on the corners. Okay. And so if you just rotate that shape, then now you have the XY or the X or the YZ. It's the same kind of motion, but in the three different combinations of the axes. Okay. Now, what about these two? These two are unique, and we typically see this in 5D orbitals. They split out 2 and 3. So the XZ, YZ, and XY stay together in terms, a lot of times, of their symmetry, and then the other two are unique. You have the x squared minus y squared. And that makes sense. These go along the axis. So think about the x squared axis. If we square the numbers on the x-axis, the negatives become positive, don't they? So the positives are positives, and the negatives are now positives, because we squared the x-axis. And so this would be positive here on the x-axis, and positive there on the negative x-axis. But the y-axis, we're subtracting y squared. So we made y squared positive on positive and negative, and then we subtract it. So we end up with negative here and negative here. So it's the same kind of thing as the xy, but it's rotated 45 degrees. Okay. Now, you say, wait a second, up here the gold was negative and down here the gold is positive. That doesn't matter because a femtosecond later these colors are going to shift, right? If it bulges that way, it's going to bulge a different way very shortly after. So this is wave nature, so you can't be so rigid to say yellow's always positive and blue's always negative. You know, they're going to swap. These things are going to blink and change color. Now this one is very strange. We've combined the x and y axes here. This brings in the z-axis. We haven't used the z-axis in this one, right, down here. So we're going to use it twice in the other one. So z-axis is 0 here, so it's 2z squared on this one. So this is really big. In this picture, it doesn't seem to be as accurate, so this should be bigger. And so we have the z-axis, and it's z squared, so it's positive on both ends. Okay, and then we're subtracting x squared, and we're subtracting y squared. Now, what is x squared plus y squared? Do you recognize that from algebra? It's a circle, right? And so we're subtracting the circle around it, and so that's what this donut comes from. So it's 2z squared minus the circle of x squared plus y squared. And so that's why these are different colors. So this would be, say, positive and negative. And so those are your 5d orbitals. Now, the symmetries of these are in every character table as well. We call them Raman, right? But the d orbitals, if you look at those character tables, you'll see something similar to all of these. The xy, xz, and yz are in all of the character tables. Those are going to tell you what the d orbitals do in that point group. So if you look up a C2v molecule and you find out where the xy is, that's going to be the symmetry of the dxy orbital. And that'll be really helpful for us in doing selection rules. Now, we did that detailed analysis of the d orbitals. I'm not going to do it for the f or the g. It's just really difficult. The functions are crazy. But here are the f orbitals and the g orbitals, and they just keep going up. Okay. And eventually, the nodes and lobes approximate a sphere again. Notice that? Yeah. So they start with a sphere and an s orbital, and then they get crazy, and then they become a sphere again. So, and that's this sort of approach to there being no wave nature. Eventually, the wave nature gets washed out. The electron cloud gets so big, and you can't detect the wave nature anymore. Okay. I've got all of the quantum numbers listed over here. So for the g orbital, that's L equals 4, and it goes from -4 to +4, and so that's why there's 9 of them. Okay, so there's 2L plus 1 orbitals. This angular momentum is the L, the angular momentum quantum number. It's really important, and it's quantized, but also the z component of that angular momentum is quantized. And so when we talk about m sub L, we're really talking about the z component of L. We don't know exactly where L is pointed in space, but we know if we put it in a magnetic field where the z component, the magnetic field component, is located. And so that's why we draw these cones. The distance to the edge of that cone is L. And we don't know where in space that's pointed. So that's why the cone sort of points out this ambiguity as to where L is actually pointed. But if we put this in a magnetic field, we can tell if it's L equals 1 or L equals 2, L equals 0, and so this M sub L would be the projection onto the z-axis. Now that would be something that we would get this splitting due to a magnetic field, and that would be called the Zeeman effect. If we split it due to an electric field, because the electrons are charged, that's the Stark effect. And if we just get high resolution spectroscopy and we see this little splitting occur naturally, what's going on? Well, the spin of the electron is like a tiny little magnet. And so it's putting itself in its own magnetic field, and that's called spin-orbit coupling. And so where the magnetic quantum number, the spin of the electron interacts with the projection quantum number M sub L, and you get these tiny little splits. And that's called spin-orbit coupling, and that's what we're doing with the term symbols. So we will get into this, we'll wade into it knee deep, and we'll be able to understand spin-orbit coupling. Now that in the hydrogenic orbitals, we'll end with this, the energy doesn't depend upon S, P, D, and F. In multi-electron orbitals, it does. Okay, and then next time we'll get into electron configurations and multi-electron atoms. So have a safe weekend.